Hey everyone, so let's talk about a force you're feeling right now and every single moment of your life, but maybe don't think about too much, and that's gravitation. You can think of it as this invisible string that's holding our entire universe together. So let's pull on that string a little and see what secrets we can unravel. From something as simple as an apple falling from a tree, to the planets circling the sun, all the way up to this magnificent dance of galaxies across billions of light years, gravity is the silent architect behind all of it. It's calling the shots for everything, big and small. But how in the world did we figure out the rules of this fundamental force? I mean, it's a classic question, right? And it seems like it has a totally obvious answer. But as we're about to find out, the real truth is, well, it's way more fascinating and kind of beautiful than it first appears. Let's keep this little puzzle in the back of our minds as we journey back in time. Okay, so our story actually begins not with the why, but with the how. Before we could even begin to understand the force itself, some absolutely brilliant minds had to first map out the patterns of the heavens with just painstaking precision. Think of this whole thing as a cosmic detective story. For centuries, you had astronomers who were like the beat cops on the street, just gathering clues, endless charts of where the planets were. Then along comes our master detective, Johannes Kepler. He took all that raw data, especially from the legendary Tycho Brahe, and he saw something no one else did. He saw a pattern, a set of rules the planets were all following. Now, for thousands of years, pretty much everyone just assumed planets moved in perfect circles. I mean, it felt right. It seemed divine and perfect. But the problem was, the data just didn't fit. And Kepler's genius was in realizing that, you know what? The universe doesn't really care about our ideas of perfection. The planets weren't moving in circles at all. No, they moved in ellipses, which are basically just stretched out circles. And this was a monumental discovery. Kepler had cracked the how of planetary motion with unbelievable accuracy. He had written the cosmic rulebook, but the reason why the planets followed these specific rules, that was still a complete mystery. And that brings us to the next giant leap in our story. So if Kepler gave us the rules of the road, the next step was to find the universal traffic law that explains it all. And this is where the one and only Isaac Newton enters the picture. This is the question that just changes everything. I mean, Kepler's laws are brilliant descriptions for sure, but they aren't explanations. There had to be some underlying force, right? Some invisible hand guiding the planets along these perfect elliptical paths. And this was it. This was Newton's huge aha moment. He connected the dots and realized that the force pulling a stone down to the ground and the force keeping the moon tethered to the earth, they had to be the same thing. There wasn't some special heavenly force and a different earthly force. It was all one single universal force. And from that one incredible insight, we get this beautiful, powerful law. Let's break it down real quick. More mass means more gravitational pull. Simple enough. But, and this is so important, the farther apart the objects get, the weaker that pull becomes. And it weakens fast. This was a total game changer. A single rule for apples and for planets. And here it is, the equation that unlocked the cosmos. Don't worry, it's not as scary as it looks. The force of gravity, F, equals g, which is just a special number called the gravitational constant, times the masses of the two objects, all divided by the distance between them, r squared. It's just an incredibly elegant piece of math that explains everything from a falling stone to an orbiting planet. Truly revolutionary. Okay, now that we have the law, let's use it to clear up something that we all get mixed up in everyday language, the difference between mass and weight. Believe me, they're not the same thing at all. So here's the crucial point. Your mass is the amount of stuff you're made of. So if we look at Rajiv, his mass is 75 kilograms whether he's on Earth, the moon, or just floating around in space. That never changes. His weight, though, is the force of gravity pulling on that mass. So here on Earth, that's 735 newtons. But on the moon, where gravity is much weaker, his weight would be way, way less. See the difference? We know gravity holds entire planets in orbit, so it must be crazy strong, right? Well, let's test that idea. What about the gravitational pull between, say, two people just sitting next to each other? Okay, so let's imagine two guys, Mahendra and Virat, sitting on a bench with absolutely zero friction. The number you're looking at here is the speed Mahendra would gain towards Virat after just 1 second, thanks to gravity alone. I mean, that is an astonishingly tiny number. This shows us that while gravity absolutely rules the cosmos, between everyday objects like us, it's actually an incredibly weak force. All right, we've got all the pieces now. We understand Kepler's how and Newton's why. We know the difference between mass and weight, so it's time. Let's go back and finally solve that mystery we started with. So why does the stone always beat the feather to the ground? Well, it's not because gravity is playing favorites. It all comes down to the air. The air creates an upward push, a buoyant force, and a frictional drag. Now, for a light, spread-out feather, those forces are huge. They fight against gravity and make it float down nice and slow. But for a dense little stone, those forces are practically nothing compared to its weight. But what happens if we could just get rid of the air? Take it right out of the equation. What if we could drop that stone and that feather in a place where only gravity is in charge? The result is just stunning. Without air getting in the way, they fall together, side by side, accelerating at the exact same rate. In a pure vacuum, gravity treats them as total equals. And this is the fundamental takeaway. Earth's gravity accelerates all objects at the same rate. It doesn't matter what their mass is. The whole illusion that heavier things fall faster, it's all caused by one thing: air resistance. Which leaves us with one final, really cool thought. We've established that gravity pulls on everything: feathers, stones, moons, you name it. So if the Earth is constantly pulling on the moon, just like it pulls on a stone, why doesn't the moon come crashing down? What in the world is keeping it so perfectly balanced up there in the sky? Definitely something to think about.